Hi everyone, I'm Mohammed Kamal and my fellow Hisham.
Hi everyone.
Here is our presentation, which basically surface around the forecasting customer loan default using the Ensemble Learning method. We got the data from the Lending Club, which is a San Francisco-based company. They basically use a lending match portal where they got applicants' information and they decided there to get a loan or not. So as you can see right here with their portal, so you can get a loan up to even up to 40,000. So by applying and they use different machine learning techniques. So here is a number of companies in the world these days use user information. They put it in the machine learning algorithm and they decide whether you are safe or risky to get a loan. So uh, the question that we started with was to determine if a consumer is eligible or not, and a scorecard approach was common standard, but we were using the assembler learning method, which is a better approach. So is that going to be a better approach or not? We're going to see together in this finding. We started from data cleaning, which is the most important and time consuming. Basically, it took us almost 85, even more than that, time we spent was on data cleaning. The data that we have are basically categorical, and we replace those missed value with NA, and also we use a chi-square analysis to understand if they are MNR, MAR, or MCAR. So when you come to the future engineering, we created future based on existing futures, and we name it the time since first credits. And we calculate the difference between the loan application date and the first credit line that was opened, and we transformed that into a false category, into a number which is a 0 and 1. 0 is people who's going to be defaulted, and 1 people who's not going to be defaulted. So it's good to lend them. And then coming to the dimensionality reduction, we ran a persona correlation matrix to find the futures redundant to improve the data quality. And furthermore, we positive and negative correlations of 75 are removed. Anything 75% are more removed, and we grade futures did not share a high degree of persona correlation despite being closely related, and we also eliminated subgrade future. All right. So the first elimination future, which have only one factor or a constant value, and for those we run multiple random forests, and also the recursive future elimination technique we also applied in our methods. And then when you come to determining the cluster, we use Clara. So basically this Clara method, we can use that way with the large data sets. And also the Shote method, we use that one to estimate the number of optimal numbers of cluster. So the normalization, we applied Gaussian normalization technique, and also we divided our data into 80-20 test and also the models into there. And these are the number of different machine learning models we applied in our machine learning algorithms, like the KNN, decision trees, random forest Simian, kernel Simian, assembler. So we're gonna show you, we have a couple of slides how well this machine learning perform. So performance wise, we use a confusion matrix, and also the accuracy based on that, we calculated how well each machine learnings perform. All right, so we're gonna go the next, which is the result part. I'm gonna give the floor to Hisham. Hisham, here is your floor.
Thank you very much, Mo. So the first thing that we did with our data set was to understand if the missing value were correlated with the feature we're trying to forecast. And what we saw is that people that were not filling the employment title were most likely to default than people that were filling it. So this value is MNRA, missing not at random. On the second important point, when we use the recursive elimination function, we found that the optimal number of features were 8. And this minimized the minimum squared error. The 8th feature that was selected using this method was the loan amount, the annual income, the interest rate, the revolving balance, the time since the first credit, the number of open accounts, the total number of accounts ever opened, and the term of the loan. On the machine learning model, when we run the forecast, we got very, very high accuracy on both the training set and on the test set. So we can see KNN with 100% accuracy, random forest with 99.9% accuracy on the training set. On the test set, results were a bit lower, but still pretty high. The problem that we saw is that when we look at the confusion matrix, and this is especially visible when you look at kernel SVM and SVM, the value 1 indicates that the model is putting all its focus on people that were not defaulting. And this is because there was a class imbalance in our data set. 85% of the individuals in our data set did not default. And machine learning model, by focusing on putting all their weight toward people that were not defaulting, resulted in some inaccuracy in their ability to forecast people that were going to default. So for example, look at SVM and kernel SVM, they're forecasting that no one is going to default on the dataset. We also try to use clustering model to improve our dataset with the idea that cluster would isolate some group of the population, and we use Clara method for that. We ran the silhouette method, and we found out that 4 was the optimal number of cluster. At the end, the final result did not really improve, nor did it increase the quality of our model. So all in all, it was a bit pointless work. Let's compare quickly all the different models versus their closest counterparts. So the first one is the KNN model against the naive bias, which both use points that are surrounding target point that we're trying to forecast. And what we found is that KNN usually performs very poorly when there's class dominance. And this is especially the case when we look at, for example, our training set. KNN has 100% accuracy, but on the test it only has 76%. On the contrary, the naive bias model still has 82.6% accuracy. On the SVM versus kernel SVM, we can see that the linear SVM has coefficients that are very close to 0. This means that he's unable to separate the data linearly, meaning the model is not very useful. On the contrary, the kernel SVM has some positive coefficients, some negative coefficients. Positive coefficients such as annual income mean that the higher the annual income, the lower the risk of default. And in contrary, the higher, for example, the loan amount or the interest rate or the revolving balance, the most likely the person was going to default. When we look now about random forest and neural network, we can see that they classify most features more or less with the same importance, at the exception of annual income, which is ranked as the most important feature in the neural network model, while it's only ranked as the 4th most important feature in the neural network, or in the random forest model. So we also did an initial study whereby we take 2 features, we create a grid set of points, and we try to forecast whether our model is gonna put the customer as defaulting or not defaulting, and this allows us to have a 2D visualization chart. It's very powerful. So for example, with the Adabus, you can see that the higher the interest rate and the lower the annual income, the most likely our customer is going to default. This is the red part on the top left. So we can also see a big red column in the middle, which is like lower fit. So we can go over all the different models, such as random forest, which has the same feature, KNN, which is a bit more different, naive bias also, high interest rate, low annual income, most likely to default, linear SVM and KSVM, which are just indicating that all variables were the same, and the neural network, which means that when there is a high interest rate and low annual income, the customer is most likely to default. So this graph clearly shows us that we need, for customer loan to default, we need to have a combination of high interest rate and low annual income. So running this across different dimensions is very interesting. However, we can say this data are not very separable, given that not any model can classify correctly the data. So we faced a few challenges, such as the computational requirement because of the large number of features. Some of the model techniques that we use require the data to complete, especially the recursive function elimination. And other challenges that we noticed was the correlation problem using feature redundancy, whereby Pearson correlation was not enough, and using a Bayesian inference matrix was an additional value to identify features that were redundant. To conclude, we used the chi-square analysis, and we found out that missing employment title was most likely correlated with default. We found out that the that the loan amount, annual income, interest rate, revolving balance, subsistence credit, number of account open, total number of accounts open, and time of the loan were important variable. We found out that the best machine learning model was the random forest with the high accuracy, and we also think that naive Bayes did a very decent job as well. Ensemble learning didn't provide any advantage, given that most models pointed out to the same output, and clustering didn't improve our model at the end. Thank you very much, everyone.
All right, thank you so much. I hope you guys enjoyed the presentation. If you guys have any question, please send us any reply. We're gonna be answered those. Thank you so much.